I love it. When you just do like motion, I'm like, again.
Yeah.
This is not.
Okay, lecture 6, sorry. Okay. And let's continue what we were talking about last time, which is the basics of qubits and how we measure them and map them to the block sphere. So just to recall, we introduced the block sphere where we have the logical basis state 0 and 1 as a north and south pole of the block sphere. The block sphere itself has unit radius. We have that polar bear and penguin type things. Okay, sorry, let me just get through this. So we have superposition, we talked about that last class, and we introduced several basis states. So 0 and 1, which are the north and the south poles. We had 0 plus 1 over here, 0 minus 1 over there, 0 plus I times 1, where I is a complex, the imaginary number, square root of minus 1, and then 0 minus I times square ket 1 is on that side of the block sphere. And we said that a qubit state is any point in the block sphere. So you can have a qubit that's at this point over here, and that corresponds to this particular superposition. You can have another, some more general superposition, which is not just entirely on the equator, but it could be somewhere, anywhere on the block sphere. Okay. And all of these we will see how to map, so how to take a state like that looks like that and convert that to a point on the block sphere. We will see that today. So in the last class, I mentioned what complex numbers are, that they have a geometrical representation, which is pretty nice, which is the x and y in the complex plane. The real and imaginary axis are the x component and the y component of this complex number. It has a conjugate, a complex number has its conjugate, which is just flipped around the real axis. And we also have the polar representation of a complex number, which is we just, instead of writing it as x and y or x plus iy, we write it as having this component r, magnitude r and angle theta with respect to the x-axis. So the real and imaginary parts I already introduced over there. And then we can use the Euler formula, which is because we see that x is r cosine theta, y is r sine theta, that's the z is equal to x plus iy. And this cosine theta plus I sine theta can be written as e to the I theta using the Euler formula. Okay, this also covered last class. So the thing that I was going to start with today is sort of some of the important phasor or complex angles and complex number values. So for example, one of the important phasor angles or important complex numbers is this one, which is e to the I 2 pi, which just means take the complex number that's along the x-axis with a unit magnitude and then rotate it by 2 pi, right? E to the I theta. And so therefore you can see that will come back to the original place. So e to the I 2 pi must be equal to 1. So 2 pi is 360 degrees. And then pi is rotation by 180 degrees. So you can see a complex number that was along the x-axis with unit magnitude is now rotated by 180 degrees. It will be equal to minus. Okay, so e to the I pi is equal to minus 1. This is a famous formula. I think, again, discovered by Euler, which is e to the I pi plus 1 equals 0. That's famous because it relates 5 important mathematical numbers, right? E, I, pi, 1, and 0. So, and also, of course, it's equal to minus e to the I minus I pi, because rotation by 180 or rotation by minus 180 are both the same. And rotation by 90 degrees will, of course, take a complex number along the x-axis, convert it to an imaginary number along the y-axis. So that's e to the plus I pi over 2 is plus I, e to the minus pi over 2 will be rotation by minus pi over 2, 90 degrees will be minus. Okay. Okay, here we covered these last class, so I won't go over them again unless anybody has a question on those relationships. So to make all this more sort of little bit more general, you can take any complex number z. I've drawn it as along the x-axis, but it can in general be along any direction in the complex plane. Then if I multiply it by e to the I pi plus or minus, it doesn't matter. That's equivalent to just rotating it by 180 degrees. So if it was along the x-axis, it rotates to be along the minus x-axis, but even if it's in any other direction in the complex plane, it'll go the other way, right? It'll rotate by 180 degrees. And similarly, the 90-degree rotations are also over. So e to the I pi over 2 is a rotation by 90 degrees in the complex plane. E to the minus pi over 2 is a rotation by minus 90 degrees in the complex plane. And of course, the 2 pi will be just coming back to itself. See, ze to the 2 pi is just the same number itself. Okay, so let's to see how much you're following this. So if I give you this complex number z equals 1 plus 3i, what's the real part? Yes. 1. What's the imaginary part? Yes. 3. Yes. What is the norm? Yes.
Square root of 10.
Square root of 10. Yes. Very good. Everybody follow that? The norm is square root x squared plus y squared. So, and the norm squared is then just 10, right? If I had to plot this in the complex plane, we're going to be doing a lot of this today. Back and forth here. Today. Okay, so in the complex plane, where is 1 plus 3i? Real part of z, imaginary part. Yes?
Set the point 1, right?
1, 3. Right. Okay, so the complex number, which as I said, usually will draw it with this arrow representing the number. Okay, and then what about the complex conjugate? Yes.
It's the same thing with 1, -3.
Yeah, very good. Drawing didn't come out so good, but that's okay. And now what if I wanted to write this in polar form? Remember, polar form is form r e to the I theta. So how do I go about, for z equal to 1 plus 3i, how do I go about finding r and theta? Get me started. Yes,
R is just the norm, which is 10.
right. We calculated that, so 10, very good. Theta, yes.
Will be the cotangent of the variable.
R you say is cotangent. Oh, sorry, theta is cotangent of 3 arc tangent. Yes. Did you see that? In just many different ways, but obviously if I write this as theta, then this is the right triangle, which has units 3 over there and 1 over here. We already calculated the hypotenuse, which is the magnitude of R, which is R. And so all we have to do to find theta is tan theta equals the opposite divided by the adjacent of this triangle. So that's 3. So theta equals tan inverse of 3. Okay. So this is how you have to go about finding the forms for different complex numbers. Yeah. Got to turn on the video. Sure. And people on Zoom see us now?
Yeah.
Okay, thank you. Bring that up. Yeah, that was a calculation. Okay. So now let's talk about measurement. So I take some general. So far we have introduced qubits. So this is like sort of the first postulate of quantum mechanics, which says that quantum systems, or all systems really, because it's a theory of the whole universe, but any particle or any object in the universe can be represented by its quantum state. We have taken a simple quantum object, a qubit, and that qubit can be represented by a quantum state, which is psi, which is equal to some superposition of 0 and 1. This is in a complex two-dimensional Hilbert space. Is basically the statement of the first sort of principle of quantum mechanics. The second principle now says, even though we have all this infinite amount of information in a qubit, right? Because a qubit can be anywhere in this block sphere. And when we specify it, we're specifying it by two complex numbers. So effectively, 4 real numbers. So it seems like we need 4 real numbers. But when we actually measure the qubit, we will always get only 0 or 1. Yeah, this is the second sort of postulate, maybe the third. I can't keep track, but whatever. It's one of the important postulates. Okay. And this is what, brings us back to sort of the classical binary logic that we introduced in the beginning. That when we measure this qubit, which always for any real computing, whatever we have to do in the end, we have to find what the qubit state is, we have to measure it. And when we measure it, we always get a 0 or a 1. But the point is that that 0 or 1 is not definite. We will only get it with some probability. Okay. How much probability? The probability is given by the norm squared of the coefficient in front of the basis state 0 or the basis state 1. So in this case, if I call this A, the coefficient in front of 0 is 1 over square root of 2, then the norm squared of that, right, which we just learned about norm squared in complex numbers, well, norm squared of a real number is just 1 over root 2 whole squared, which is 1 over 2. So the probability to find the qubit in the state 0 is half. Okay. And the probability to find it in the state 1 is now the norm squared of 1 over root 2 e to the I pi over 6. Okay. Now, what is the norm squared of that? E to the I pi over 6 divided by square root of 2 norm squared. What is that? Yes, 1/2 also. Do you understand why? Because the norm of e to the I pi over 6, do it once. So but if I write over here, at what point does my writing become invisible to those of you over there? Only if I'm over here.
Yeah.
Okay, but if I'm here, it's okay.
Yeah.
Okay, all right. Let me know at some point if, I'll put this as a line just to remind myself not to go on that side. So e to the I pi over 6 divided by square root of 2. But I mean, I'm just going to say any e to the I theta. Okay, this is the general form of that coefficient in the second in front of 1. But okay, I'll just do this one first. So the norm squared of this, well, if I'm given a complex number z, how do I find its norm squared? Any general complex number. Yes.
Multiply by the complex conjugate of z.
Excellent. So I take z and I multiply it by z squared. That gives me the norm squared. Right? So same thing over here. I'm going to do e to the I pi over 6. And now the complex conjugate of e to the I theta is e to the minus I theta. Then in the denominator is just root 2. So again, this cancels. I get e to the 0, which is just 1 divided by 2. And so you can also see for b e to the I theta, where b is any real number, as long as this is real, and this is theta is always generally assumed real. So e to the I theta is, a complex number just like this. Then the answer is exactly the same. B e to the I theta times b e to the minus I theta. Okay, so it's just b squared. So if I can write the second coefficient as a real number times e to the I theta, then the norm squared is just the square of that. Okay. And in this case, as we just discussed, probability of 0 is half, probability of 1 is also 1/2 in this case. So now you can see that 1 over root 2, why we write it like that in these cases. Because the sum of the two probabilities, probability to be in 0 and the probability to be in 1, well, for a qubit, assuming that those are the only two possibilities, we want the sum of those two to go to 1. Right? Because we want the qubit always to be in one of those two states. So that's why we have to put the square root of 2. Even when we did all the other examples last class, we took those basis states to be 1 over square root of 2, 0 plus 1, 0 minus 1, 0 plus I1, etc. It's the same reasoning. Okay, and now for something more general like this, well, nothing magical about this one. You can verify for yourself if you calculate the square of, I encourage you to go back and calculate this, but it's pretty straightforward. You'll get each of those to be some value. And the answer will be, again, summing up to 1. So the next kind of interesting question to ask, any questions? Sorry, go back here. Is this, do you think you can do this on your own? I just made this up. So you should be able to figure it out. Maybe you want to try now while I'm here. So what is the norm? What is the probability of 0? Or maybe simpler is what's the probability of 1? Yes.
1 quarter.
1 quarter, right? So presumably the other one should be, yes, how much? 3 quarters. So you need to verify that. I had to contract it to fit it, get it to fit, so it may not be exactly 3/4. It should be closer. Okay. So let's say that we get 0, right? So I just told you that when you measure the qubit, there's a probability of getting 0 or 1. Okay, but let's say after you made the measurement, you know what it is, correct? You know, let's say you got a 0. Okay, so now the qubit is in the state 0. Suppose I now measure again, what's the probability of getting 0? Yes, 100%, exactly. And the probability of getting 1? 0%. Okay. It may seem trivial to say this, but this is important. Okay. Once it is in one of those basis states, and if you measure again along that basis state, okay, by now when I say along, hopefully it's clear to you, along that north-south axis, of the block sphere, right? Once I measure along that and get a result along that axis, either 0 or 1, if I measure again, I'm always going to return the same state, okay? Whatever it was I measured the last time. So repeated measurements, once I'm in that basis state, give me back the basis state. Okay? This will be important in a minute when we do consecutive measurements. But so, okay, this just summarizes what I've already said, really. So we say a qubit state is normalized if the total probability of the measurement along any basis, whether it's 0, 1 or plus, minus, whatever, is always 1. Okay, the total probability. And we require this to be true. So if you give me a qubit state, I must first check that the qubit state is normalized before I start to do other things with it. Okay. And sometimes we'll need to multiply by a constant to make this true. Somebody may write down a qubit state, or I may be careless, forget, to write down these things carefully, which I will sometimes. And then you should say, oh, wait a minute, that's not normal. So if I consider some state like this, I just made this state up, square root of 5 times 0 plus I times 1. Okay, here's a state. Well, it's not normalized, right? You can see that right away. Right. Square this, it's 25. No good. Okay. So we have to normalize this by multiplying it by a constant. That's the usual way, at least, that we do it. You could think, oh, why don't I just subtract something or whatever? But that doesn't really work. It doesn't preserve the state itself, the behavior of the state. So by multiplying it by a constant, this phi, as you can see, preserves sort of the initial state, except for that extra constant, this multiplication. And now we have to find that multiplying factor. Hopefully it's pretty obvious to you how to do that, but if not, we'll just go to this particular example. Phi was written as square root 5 times 0 plus I times 1. And now to normalize it, that is, I want to write the state psi, which is a real qubit state, as A times 1. And this is just A times square root 5, 0 plus A, yeah, A is outside, so plus I get 1. So if I write this out, that's just square root of 5 times A times get 0 plus I times A times get 1. Okay, so that's our new state. And now to normalize this, I'm going to demand that the norm squared of this and this must sum up to 1. So if I norm square of this, that's just so modulo squared. I'll sometimes say mod squared, instead of norm squared, but hopefully that's 5A squared. Okay, by the way, we always require this A to be real. Okay, we're not going to multiply by yet another complex number. plus non-squared of this whole thing is plus I a, which is just a squared again, plus modulo of non-squared of I is 1. So we get this is equal to, did I get that right? The square root of 5, right? Or did I write 5 there? I can't remember. What did I have in the? Oh, yeah, it was a square. Oh, so I said wrong. I thought it was a 5. Okay, 5a squared plus a squared, which is a 6a squared. Fine. Okay, so a is equal to, and this must be equal to 1. We are requiring, this is our condition, that we are requiring that everything be normalized. So therefore, a equals 1 over square root of 6. So our qubit state psi is equal to square root of 5 divided by 6 times 0 plus I divided by square root of 6 times. So this one is properly normalized, so it can be used as a qubit state. Yes.
I like this is so we square both root 5a, you get 5a squared and IA.
Yeah.
Should it be minus a squared? You're squaring I.
No, it's mod norm squared. It's not just norm of I squared is not equal to I squared. So I squared is I times I, which is minus 1, as you said. But norm of that is I times I star, which is complex conjugate of it. So that gives me back a 1. Good question. Thank you. Okay. I squared equals minus 1 modulo I squared equals 1. Okay. And so in a way, what we have done, what actually we should have said when we talked about this is just a little aside caveat, or what do you call it, like a little detour. Just to say that if you are thinking about vector spaces, if you know anything about vector spaces, then really what we have said is qubits are defined as an array in 2-dimensional Hilbert space. Multiplication by some constant is only there to like keep the whole thing normalized so that it stays on the unit block sphere. But in some sense, all the information about the qubit, this relative ratio between the amplitudes and the coefficients or whatever, these are also called amplitudes, by the way, things that in front of 0 and 1. And the ratio between them or the phase difference between them, all that is captured, in any state, but we specifically want to restrict ourselves to those that are normalized for the qubit states. Okay. But any state along a ray, along the same direction as our qubit state is equivalent in some sense, because it's just multiplication by some convenient constant. Okay. So now we don't just have to measure in 0 or 1, we can measure in other bases. So remember we said last class that yes, we have chosen the north-south axis somehow to be our logical qubit basis or our computational basis. So whenever our computer measures the qubit, it will usually give a result 0 or 1. Okay. But that's not necessary in quantum mechanics. I could measure along some other basis. The reason is this block sphere is not like really a planet, right? It has no like continents or anything on it to tell us what is north and what is south. And it's not spinning, right? It's not like it has some axis around which it's spinning. It's just a geometrical construction. So if I rotate everything by 90 degrees so that the x-axis becomes the north pole, right? The north-south axis. Now that's just as good a computational basis if I wanted to do it that way. And later we'll see how to switch between bases with like unitary gates. But for now, hopefully you can see that just rotation by 90 degrees doesn't make a difference to the sphere. So we could now choose to measure along the x-axis. Okay, or we could, rotating by 90 the other way, we could choose to measure along the y-axis. Okay. So let's understand how to go between different bases. So, okay, this just summarizes all that. So what do I mean by a basis? It's just a set of distinct measurement outcomes. So when I measure along the north south axis, that's a 0 or 1. That is, that just is one basis. Okay, it's one of the bases. If I measure along x or y, I call that plus or minus, right? I get a plus or minus state coming out. Okay, result coming out. And that just means I'm measuring along the x basis. And I can also measure along the y basis, I'll get plus I or minus I as my result. Okay. So we just call each of those bases, just according to this, corresponds to measurements. X basis corresponds to measurements in the plus or minus set, y basis to plus I minus I set, and z basis for measurements along the 0, 1 axis. So now let's just consider how to go between the different bases. Thanks. 3, 2, 0. You chalk. I'll go wrong.
Good things.
Huh?
I've other professors have been like talking about their new shop too.
Oh. Is this for everyone? Like, or just somebody left theirs behind? Yeah, you see that's what they Crayola chart. Interesting. This is very nice. Okay, so this was our state. We already know by now z basis measurement. How to do that is very straightforward. We just take the norm squared. So probability, I'll just write probability of getting a 0, right, is just 3 over 4. And probability of getting a 1 is 1 over 4. And the two of them sum up to 0, to 1. So we know this is a good quantum state. Now to measure in the x basis, we know that the states plus is equal to 1 over square root of 2 times ket 0 plus ket 1. And the state minus is 1 over square root of 2 ket 0 minus ket 1. So if I could express this psi in terms of plus and minus, then our problem would be solved again. We would just have to take the norm squared of the coefficient in front of that plus and minus state, right? Okay, so to do that, well, hopefully, but straightforward, you see it right away from looking at this, that if I add these two states together, so if I do a plus sign over here, adding ket plus and minus together, well, the plus sign and minus sign over here, so the ket 1 goes away, and I'm left with 2 times square root of 2, which is just square root of 2 times ket 0. So we get ket 0 is equal to 1 over square root of 2 times ket plus ket minus. Similarly, you can write by taking, you subtract the two states, you'll get 1 over square root of 2 times plus minus minus. So you see this plus minus and 0, 1 are very symmetrical with respect to each other. Each is just this nice linear combination of the other, right? Everybody okay with this? What I just did? Later we'll see that this is also easy to do using inner products or something like that. But for now, this simple idea should hopefully be enough. Okay, so now I look at that state that I had psi over here. I substitute ket 0 is this combination over here. Substitute 1 is 1, not minus. Substitute 1 is just this linear combination over here. You can see the algebra is a little bit full, but it's not difficult. We'll go through it this time in some detail. If you've never seen this before, it may be helpful. 1 over square root of 2 times ket plus ket minus. That's for the state 0. Then for the state 1, I have 1 over 2 times state 1, which is 1 over square root of 2, ket plus minus ket. So now I bring together all the terms that have plus in them. Okay, plus that is there in front of them. So that gives me root 3 plus 1 divided by 2 root 2 times ket plus. And then root 3 minus 1 divided by 2 root 2 times the state minus. So the probability of measuring plus is just the square, the norm squared of this coefficient, this amplitude. Remember, this is, I'll also call this amplitude sometime, which is just root 3 plus 1 divided by 2 root 2 norm squared, which is all, since it's all real numbers, this is plus I recognize. No, it was just okay. I'll do one with I. Okay. So yeah, I mean, obviously you can put this in your calculator, or you can just, like the denominator is 8, the numerator is 4 plus 2 square root of 3. Okay, yes. Yes. Okay, so I have to work that out. So just in your calculators. Yeah. And the same, obviously, the probability of 1. No, probability of minus state, minus result is norm squared of that one, which is 4 minus 2 square root of 3 divided by 8. And just to verify that this is indeed a good state, I just take the sum of these two, right? And you can see the plus 2 square root of 3 minus 2 square root of 3 cancel. I get 8 divided by 8. So that's 1. I guess I could pull out some common factors and make this a little simpler, but basically that's it. Okay. All right. Now let's do probability in the y basis. So plus I is 1 over square root of 2 times 0 plus I times 1. And then minus I is 1 over square root of 2, 0 minus I, 1. Again, same trick, add them up together, I get plus I plus minus I is equal to root 2 times 0. So that gives me, again, by the same And 1 is just the same thing with a minus sign. Okay, so coming back to our state psi. Again, I'm going to carry through the procedure. 0, psi equals root 3 over 2 times 0, which now 0 is 1 over square root of 2 plus I plus minus I. And it's 1 over square root of 1 over 2. It was 1 over 2, right? Yeah, 1 over square root of 2. We have to be careful there. Okay. Again, combining factors plus I and minus I, root 3. Oh, sorry. There's a factor of I in front of us. In front of the 1. Because the 1, when I subtract over here, okay, I'm going to have everything is the same, but there's a factor of I that carries through, right? So that's going to be root. Okay, let me. The result here is an I over 2, but in case it's not, can I just write it up here maybe? It's off to the side. So just coming up here, get 1 is 1 over I square root of 2 times plus I minus yes. Yep, that's just when I take the subtraction of these two, there's an I that is in front of each of those ones. Okay with everyone? Factor of I. Okay. So now we see the one other sort of complex number fact is that for the same reason that I squared is equal to 1 is minus 1, right? That means I times I is minus 1, which means I equals minus 1 over I. Right? Or minus I equals 1 over I. So having an I in the denominator is equivalent to having a minus I in the numerator. Right? So this part here, I'm going to write as minus. So again, we could write this as minus I divided by square root of 2 times plus I. Okay. So that gives me something that looks just like our previous result, except that now we got a root 3 minus I divided by 2 root 2 in front of the plus I. And we got because the minus I is outside, this becomes plus. This is root 3 plus I divided by 2 root 2 times minus I. You can see you have to be a little bit careful with all these signs and so on. Make sure you get the right answer. Okay, now we can find the probability to be in the plus I state. Now we have to take the norm squared of root 3 minus I divided by 2 root 2. This time we do have to be careful, right? Because it's root 3 minus I modulo squared. Well, that's actually quite easy. It's just 4 over 8. Because the norm of x plus iy is x squared plus I squared. Norm squared is x squared plus I squared. So that's just 3 plus 1, right? and then the denominator is 8, so this is just 1/2. Just leave this here. So you can see the probability to be in the plus state over here was slightly greater than half, right? Because there's a 4/8 here, but then there's this extra term over here, which makes sense because, as I'll show you again in a minute, that thing is more oriented towards plus x than minus x. Okay, we'll come back to that in a second. But on this scale, the plus I, same thing with the minus I, probability to be in the minus I state. That's just again modulo square √3 plus I divided by 2 √2. And that is again 4 divided by 8, which is 1/2. So it is equally probable. And you remember when we go back to the original 0 state, it was also more probable to be in 0 rather than 1. It was 3/4 probability to be in 0 rather than 1. Okay, so going back, any questions? Yeah.
So I just wanted to clarify real quick.
Yeah.
The reason we did a lot of that is because now that we have like probability of being on the plus side on the x-axis and the plus I side on the y-axis, we don't need to find the minus side or the minus I side, we can just subtract one.
We could, yes. I explicitly calculated it.
Okay.
Wait, was your question? I found the probability to be plus was here, and I did write down the probability to be in minus over there.
I got lost somewhere.
Oh, okay. Yeah, I had written it somewhere. Sorry, it's gone now. But it was just 4 minus 2 √3 divided by 8.
Yeah.
So it was pretty much the same thing. It just had the minus sign there. So yeah. So the sum of those two also added up to 1. Okay, but it was more oriented to plus than minus. Calculation, talked about this. So just coming back here again, this is what I was trying to say. You look at this quantum state, you can see, it's sort of closer to the plus x than it is obviously to the minus x. Minus x is back there. This one is closer to the plus x. And similarly, you can see it's closer to the south pole than it is to the north. Oh, sorry, the other way around. North pole than the south pole, right? Tilted up the upper hemisphere. It's tilted to the northern hemisphere, if you like. More polar way. But as far as y is concerned, it doesn't care. It's equally probable to be along plus y or minus y, or plus I or minus y. Yeah.
Can you measure in one of the bases?
Yeah.
Would it then still have the same characteristics or would they change?
Well, we just talked about it. We said once it's in that basis, once we have made a measurement and we have found the answer to be in, say, plus y or minus y, now it's a plus y state, for example.
Okay.
So it's indeed, its characteristic is now different than it was originally. It's now a plus y state. And we'll talk about that in a minute. What happens if I measure again in some other basis? That's important. It's an important question. Okay. Is that clear? And this idea of projection is actually very helpful. So just think about that mentally, right? Like once I project it onto this x axis, it becomes an x state. It has forgotten what its previous angle was with respect to the x axis. Once I projected it onto the y axis, it has become a y state, either plus y or minus y. It's lost all memory of its previous state, that it was in this other combination over here. This is very important, as we'll get to in a minute. Okay.
What the state goes for?
Yeah, we'll come to that in a minute. Yes. Okay. Yeah, there's the calculation. All right, so I can do this for arbitrary basis systems. Okay. As we were just saying, it doesn't have to be plus y minus y, plus x minus x, plus z minus z. It can be anything. So I choose some other basis states. I've just written them over here. I chose them. I chose any two states which are at antipodal points on the block state. Antipodal just meaning opposite, right? Like on the globe. Like if I were to go right, drive a hole right through the center of the earth to the other side of the earth, that would be my antipodal point, right? And so these 2 points on the block sphere can serve as a new basis. Any two such points that are at opposite ends of the block sphere can serve as a new basis state. And we can calculate the probability for our original state. So if I call these states as A and B, A is above the equator in the northern hemisphere, B is below the equator in the southern hemisphere. Okay. And now we can take our original state, which I've also drawn here. This is our original state, the one that we just calculated all these things for along the different axes. And now we can measure it along these basis states. We can find the probability to be along these basis states. How do I do that? Again, it's nothing but sheer algebra working through all the different possibilities. I know this may seem a little bit boring, but I'm doing it really slowly this one time. And then later on, as we get through the rest of the course, and we'll teach some other techniques. Okay, and this will switches. That switch. Okay. So once we get through this, I will be able to hopefully not next class, but sometime once we introduce linear algebra, you'll see that these calculations become a lot easier. But for now, I'm doing it really slowly so that you know, even without linear algebra, we can do these calculations. It's just much slower, takes more time, etc. But it's not anything more complicated than just this whole process of finding the combinations that give you 0 and 1. So again, looking at it's like solving linear equations, you know. Sure, you did all that in school at some point, and you did it, and it's slow and it's boring, and you do it a few times so that you know how it does, and then you program it into your computer and never worry about it again. Right. So that's probably what we'll be doing soon. Okay, so let's look at the states. So the original state is the same, and now the new states, A is root 3 over 2, 0 plus I over 2, 1. Oh, it's on very convenient. A equals root 3 over 2, 0 plus I over 2, 1. Okay. And this one, B, is I over 2, 0 plus root 3 over 2. Just give this. Okay, so now I need to find 0, some linear combination of A and B. Any suggestions? What can I do to the equations to get me my 0? I want to get rid of the 1, right? Yes.
You could multiply B by like I rad 3 or something.
Very
Sorry.
nice. Yeah.
I rad 3.
Multiply by I. Okay. And up here, I rad 3 gives square root of 3. Okay.
If you do on B, if you just multiply by I rad 3, I think then you can add them together and it works.
Let's see. Very good. Square root of 3i, multiplying and then adding them together. Right? Okay, very good. Let's see if that works. So A on this side is A plus square root 3I times B. The right hand side, okay, I'll ignore the zeros for now. We know it will be something complicated. But let's see if we cancel out the 1 things. So I got an I over 2 in front of the 1 from here. And then I get a root 3I, adding them, that gives me a 3I over 2.
Oh, wait, you know what? I think I eliminated the zeros instead of the ones.
Well, let's see if that's true.
Okay.
Okay, this gives me root 3 over 2 from the first one. And the second one gives me minus root 3, because I times I is minus 1, right? Minus root 3 over 2. And indeed, all right. That eliminated my my state 0. 0 is gone. Okay. And here I'm left with 2 times I. Right? Times 1. So therefore, my state 1 can be written as 1 over 2I, which is the same as minus I over 2 times ket A plus square root 3I times ket B. So since we have an I in there, I'm just going to make all this as, simple as possible by taking the I inside. I get minus I times A plus square root of 3 times minus I, which is just square root of 2. But minus I squared is 1. Okay, so we have done the first job, which is to solve for 1. Okay, we can also solve for 0. Right? So let's see. Suppose I multiply the first by root 3. Oh no, I want to multiply by this one by I and this one by root 3. That'll give me an I root 3 over 2 and an I root 3 over 2, and I subtract. Right? I think that's right. So if I take, so I call this equation 1, 2. So 1 times root 3I. No, what did I just say? Sorry. Multiply I times equation 1 and subtract root 3 times equation 2. Let's see if that's correct. So on the left hand side, I get I times A minus root 3B. On the right hand side, did I just eliminate 0 again?
I think so.
Oh, sorry. Okay. I wasn't trying to do that. I was trying to eliminate 1, wasn't it? Okay, let's see.
I think it's multiply A.
Oh, I said multiply this by 3, root 3, and this by I. That's all right. 1 times root 3 and minus I times square. Okay. So the left hand side is root 3A minus IB. The right hand side, let me leave the 0 for now. Let's make sure 1 gets eliminated. 3 pi over 2. Then subtracted minus I root 3. Yes, so 1 does indeed get eliminated. Very good. And now I just need to find out what happened to this part. 0. So root 3 times 0 is 3 over 2. And then minus the I minus of I squared is 1, so I get 3 halves plus 1 half, which is just 2. So I get 0 equals root 3 over 2 a minus I 2. Okay, everyone okay with that? And now that we have done that, the rest of the procedure is exactly the same as the previous 3 cases. We substitute for 0 and 1 into the state psi. State psi, if you remember, was just root 3 over 2, 0 plus root 3 plus 1 half 1. And so I substitute now for 0, that's root 3 over 2 times 0 is root 3 over 2a minus I over 2b. Then plus 1 half for 1, I get minus I. Oh, minus I over 2 a plus 3 over 2. Okay, now collecting all the terms in front of a, we get 3/4 or 3 minus I divided by 4. And here, we're going to get square root of 3 is 1 minus I. Something great. You got some? Well, let's calculate the probabilities. If you're wrong, it will become very obvious. Probabilities don't add up to 1. Maybe I made some mistake in the algebra. Always possible. When you're keeping all track of all these numbers. Probability to be in A is modulo 3 minus I over 4 squared. So that's just 4 divided by 16, which is 1/4. Probability of B times 1 minus F. So square root of 3 divided by 4, 1 minus I, modulo squared, would be 3, modulo of 1 plus I is 2. Yeah, this is wrong. Okay, what did I do? Oh, sorry, it's 2. Square root 3 over 2a minus I over 2b. Looks right with the answer. Okay. All right, I'll sort this out for next class. Or maybe you guys will find a mistake before. Meters, correct? So that's the factor of 3%.
There is a 3 minus square root of 3i.
Oh, here,
When you substitute 0
substitute zero.
in each
Zero
time.
is, you're saying this is wrong?
Yeah, I think 3 minus I over 4 is 3 minus
Square root of I
three
three I.
I over 4.
Why is that?
There. Probability of A is equal to. Yeah,
Yeah, but I don't know why.
Yeah, because
Did I do something wrong here?
yeah, when you substitute 0, I think there was a square root of 3 multiplied by I.
For zero, we said multiply A by root 3 and subtract I times B. And
I can show you here.
yeah, I'll have to put the equations down again for A and B. Solve it. Okay, this is good. It shows you that I'm not perfect and you're not supposed to be either on this. And you can also see why we move away from this later on. Okay. In principle, yes, you can do it. Except I'm incapable of obviously multiplying, right? Okay. All right, I'll figure out what the problem was with that. Okay. Next class. I worked it out on a piece of paper in my office and it all worked out. So something went wrong as I was redoing it here. I'll have to go back and refer. I should have brought that piece of paper. Okay. In the last 5 minutes, I want you to consider this interesting sort of puzzle about consecutive measurements. Oh, definitely was right. So unless I made a mistake in writing down the amplitudes this time. Okay, so the question that I want you to ponder is, we just discussed that after we measure the qubit in the z basis, we'll get the state 0, right? And 0, we just saw when we were doing the calculation that 0 is an equal superposition of plus and minus, right? So 0 equals 1 over root 2 plus 1 over root 2 minus. We saw that a couple slides ago when we wrote down what plus was a while ago. So if I measure along the x basis, what do you think I'll get? What's the probability to be in plus x? Once I'm in the state 0. What's the probability to be in the plus x? Yes? 1/2, very good. And the probability to be in minus x is also 1/2. Do you see that, everybody? Everybody okay with that? So now let's say I got plus x. What is the probability of getting 0 again? Yes? Okay. Everybody is clear on that, right? That's quantum mechanics. That's what quantum mechanics says. I measure along 0, I get 0, right? Measure along plus x, I get plus x with probability 1/2. I measure back in z, that is along the 0 and 1 axis. The probability is now 1/2 again for getting 0. Yes.
So when I measure like any kind of qubit, it doesn't collapse all the axes.
Very good. Yeah. So this is the weirdness, right? Because I have a naive picture of what's going on. I'm a simple person, right? I'm going to say that the qubit has something, a property. When I measure it in the z basis and I get a 0, I just say, well, yeah, I mean, that particle has the z-ness property that is 0. It's equal to 0. So I assign, like as physicists, we love to measure things. We say, okay, z measurement is 0. Now it's 0. That's it, right? I don't have to worry about this again. and measure along X, I got plus. Okay, so the qubit can be described by two numbers. One is the X property, which is plus, and the other is the Z property, which is 0. This is how we think about all things when we measure them. Once we measure them, they're fixed. They are a measurement. That's it. It's done. So, but that's our problem now. If I measure along the Z and I get 0, measure along X, get plus, and now in this naive model, if I measured Z again, my property has already been fixed to be 0. Right? I should get 0 again. But no, I get 1 sometimes with probability half. Okay? So this is where you throw up your hands and you're like, quantum mechanics doesn't make any sense. Right? And yes, it is true. For our classical intuition of what's going on, it's completely nonsense. Right? There's no way that something that I measured once should have now become something else again after a while. Right? I mean, you know. So, okay, so I'll end this lecture, but what I want to say to look forward to, the weirdness is useful. We're going to see how I can use it to construct an efficient bomb detector. Okay, all right. Next class. Have a good weekend.